Are you ready? Here we go. Go to this page. We are going to be doing increasing, decreasing, and the first derivative test. So with the increasing and decreasing functions, they're very common sense if you can see them. So if you can see the interval that you're looking at, if a function's y values are going up or you're going uphill, you must be increasing. Makes sense. That's silly. Of course I am going increasing if my y's are going up. Obviously I'm decreasing if my y's are going down. And obviously if there's no change, I'm constant. Those are the only three things that can happen on an interval for any function. They're either going up, going down, or it's constant, right? The problem is you're not going to be seeing the function. So we have to figure out how can you figure this stuff out when you can't see whether it's going uphill or downhill. Well, on this one, it's obviously going uphill. It's increasing, correct? But the derivative is what I'm looking at. What's the derivative everywhere on an increasing function? It's always going to be what? Positive, exactly. So if I can find a derivative and find where it's positive, I know when the function's increasing. Likewise, if I can take a derivative and find where the slopes of those tangent lines are negative, I would know where it's decreasing. If I could find where the slope is 0 across an interval, I would know where it is being constant. So this is all about the derivative and where the derivatives are positive, negative, or 0. But again, like example 1, if you can see the function, it's almost an insult to your intelligence, because if you're going uphill, it's increasing. If you're going downhill, it's decreasing. And I feel like I'm in elementary school. But when I remove the graph, it becomes a lot bigger issue. This is obviously increasing from here to here. Is that a negative 3? I think it is. From negative 3 to 1, union, nothing. It's only increasing on negative 3, 1. It's obviously decreasing from 3 to 5, that open interval. And I'm obviously constant on that little chunk between. That was so easy because I could see it. But you aren't going to be able to see it. So that's what we're going to tackle on the next page. If it is always going up, like this function on an entire interval, you're always climbing or always falling, we call that a monotonic function. Monotonic. You don't really need to know that, but it's just a piece of vocabulary that actually won't come into play anyway. So let's go to the next page. So how can we, without a graph, figure out where the function's increasing or decreasing or staying constant? And you can kind of guess where I'm going to go with it, right? What am I going to be finding? Derivatives. But I got to be careful because I just don't want to stab around on the function and plug just any old numbers in to see if it's going uphill or downhill. I need to have a system. So what my system is going to involve is what values of x will there be a change from increasing to decreasing? Because if I can find those, then I would know, well, I was going uphill all the way to here, then there was a change, and then I'll look at here. So I'm going to look at where the graph or the function actually gets divided and changes. And you got to think about where that can happen. That can happen at critical values. There can be a change in the functions increasing or decreasing. What is a critical value? One of two things. Where are what? Nope. That's relative max and min. What is a critical value? I mean, absolute. Where what happens? Go ahead. Derivative equals 0. So anywhere where the derivative equals 0 needs to get looked at. Or where the derivative what? Doesn't exist, and it could either be, I'm glad you said cusp, because it's not necessarily a cusp. It could either be a cusp or a horizontal tangent line if your derivative doesn't exist. So one of those two things. Then it says, if you don't have a continuous function, you can still change sign at a discontinuity. Where are discontinuities on a graph? Two places. Where there's a gap, but that's a continuous, so what was that? Vertical tangent line is where the derivative doesn't exist. Asymptotes, right? You can change from increasing to decreasing at an asymptote, can't you? And also at like holes, and so we're going to have to look at lots of different particular places, but they're easy to spot. So what we're going to do is we are going to make what I like to call it a sign line. we're going to make a sign line for the derivative where we're going to analyze without looking at a graph where the function is going up, down, or staying the same. So the first thing you do when you look at the function is you actually look for any discontinuities because they're important. Does that function have any issues anywhere? No. What that means is there's no asymptotes, there's no holes, there's no gaps. It's pretty, and I'll never lift my pencil. Fair enough? It's continuous. So let's write that over here. There are no discontinuities. That's important. Because if there was one, I'd need to look at that. No discontinuities. So the next thing I need to do is I need to go find, is there anywhere where the derivative is 0 or doesn't exist? So I just go take the derivative. For all of these, you will take a derivative. The chapter's called Applications of Derivatives. So we have 3x squared and then minus, and it'd be a 3x. Now, I'm looking anywhere where the derivative equals what? 0 or doesn't exist. But again, that one gets chopped off. Why does the derivative exist everywhere? Yeah, there's no denominator. Exactly. What that tells me, by the way, when the derivative exists everywhere, it tells me there's no cusps and no vertical tangents. The original function deals with the asymptotes. See what I mean? There's 3 places where derivatives don't exist. Where are they? Discontinuities, cusps, and vertical asymptotes. The derivative is at vertical tangent lines. This one does the cusps and the vertical tangents. The original deals with the asymptotes. See, it's a fine difference. All right, let's go up here. I want to know where it's 0 because it exists everywhere. So I factor. We always factor in here when we're looking for zeros. And I find that there are 2 points of interest that I need to consider. What are they? 0 and 1. And so what I do now with 0 and 1 is I know that my derivative is 0 there. And everywhere else, I don't have any issues. So I go to 0, and I'm going to put a 0 above it because that's what my derivative is. Label this, by the way. Label it f prime. I'm going to go put 1 on here. And since I've got a continuous function that doesn't have any issues anywhere and has a derivative of 0 at these 2 places, if one number over here has a positive derivative, they all do. Because the only time it could change is if it went through 0. Does that make sense? So you find these first, and then you just do a little test. You pick your favorite number over here, and you plug it into the derivative. Let's go right there's my derivative, and you see what happens. Pick -1. You'd have a negative times a what? Negative. What that tells me is that function was climbing, and then it hit 0. And now I have to decide if it continued to climb or if it turned. So all I do is I test my favorite number in here, like a half. If I put in a half right here, I'll have positive times a negative for those 2 factors, so I'm at a negative. So what that tells me is it was going up, and then it went back down. So then in the last one right here, pick your favorite number. It's going to be positive times a positive. Now I can easily answer the question. So the original question was increasing, decreasing. So it was increasing on the interval from -infinity to 0, union 1 to infinity. And you guys can write where it was decreasing. I'm running out of space. Where is it decreasing? On the interval from 0 to 1. It's easy, but all the details matter. This is what generally happens is I get a chunk of people who all they do is set the derivative equal to 0, and honestly, half the time you're going to get the right answer, but the other half of the time you're going to miss stuff. And what is a half out of 100? 50%. See what I mean? So that is a huge part of it, but it's not the only part. Watch. Right here it says, just because the derivative equals 0 does not necessarily mean that you go from increasing to decreasing. It's important that you test each interval. It doesn't always alternate like this. Here's a case in point. Had you done the derivative over here, what would you have had? Positives or negatives? Yep. What would you have had right here? 0. What would you have had over here? Positive. So it's very possible that it was going up, plateaued, and continued to go up. That is called, it gets a name. Sometimes it's called a saddle point, and sometimes it's called a plateau. What you really need to know, though, is it doesn't always change sign at a critical value. You have to run a test. So on the next page, let's go take a look at what we've got going here. We'll go find this one, same thing. I just want to know where the function's increasing or decreasing. So in my head, I'm thinking increasing or decreasing. I need to make a sign chart. Let's go put that down below. Let's go right here. I need to analyze the derivative of the function. But I need to break my sign chart up. I need to know anywhere the function's not continuous. Is that okay everywhere? Yes, usually it is, but when it's not, that's when you're going to screw up. So this has no discontinuities. Again, let me repeat what that means on your graph. You don't have any asymptotes or holes. All right, next step, I'm going to take the derivative. All right, so I go up here and I go f prime of x equals, and I just take a nice easy derivative, negative 2/3 x to the subtract 1. And I get negative 2/3, and then I get the cubed root of x on the bottom. My original function didn't have an issue, right? My derivative has an issue, though. Where? Okay, that has to go here. What that means is one of two things happens at 0. It's not an asymptote or a discontinuity. So the only options are there's either a cusp there, I'm going to go draw a little cusp, or there's a vertical tangent. Because again, when there's the 0 in the denominator, the original is the asymptote. In the derivative, it's one of the other two. And you might say, how do I know which one? The answer is, it wouldn't matter if you didn't, but it means you really get it if you do. So let's go up here, because you're going to test either way. Watch. So I go test over here. I pick my favorite number, and where do I plug it in? Derivative. Pick your favorite number, -1, go stick it in here, and all you're looking for is the sign. Will this end up being positive or negative? Positive, yeah, because the cubed root of -1 is negative, and you have a positive. My function was going up, then it has an issue. I'll know the issue in just a second, the minute I test the other side, because if it continues to go up, there, I just saw a light bulb. It doesn't matter that you get that. Honestly, it took me about a year of teaching it to actually get the details of what was going on here. We just make the sign chart and we'd get the right answer. It's increasing, decreasing. But what happens here is actually important in terms of do you really get it. So when I go test over here and pick my favorite number like 1, I get a negative. Now I know which one it was. I knew there was an issue. What issue is it? It's a cusp. Do you see what I mean? But I'd still answer the question right even if I didn't know that, because I would say it's increasing from -infinity to 0, and it's decreasing from 0 to infinity. You will never be asked, is there a cusp there or a vertical tangent line? But the fact of knowing which one means you really get it. So the graph of it, I think, is already in your packet, and you can see exactly that happening. It increased to 0. There was an issue in the derivative, not the original function, and then it decreased. Again, what would I have there if there was an issue with the original function? An asymptote or a hole in the graph? Okay, so the original function has different meaning. All right, so now we're going to talk about where relative extrema occur. In one of two places. Right here is what we call a relative maximum, right? What's the difference between relative and absolute? Because it matters. So let's talk about that for a second. How do you get absolute extrema? What do you do? It's the absolute highest and absolute lowest. And what do you do to find it? What do you test? Critical points and the endpoints, and you make a table. You don't make one of these sign charts. Do you see how you're going to might get that goofed up on a test based on what it says? If it says absolute, it means what's the highest this is. So you say it's either here, here, or anywhere it turns, and you make a table, right? And you plug all those into the original function. If I say where are the relative extrema, that's what's going to happen next. Look what happens at any relative extrema. Right here, right here, right here, right here. Something happens at each one of those. It has nothing to do with the endpoints. Those can't be. So if you start testing endpoints when it says relative, you're trying to memorize things. If you really get it, on these intervals, look what happens to the derivative. It was positive, then it went what? negative. It was negative, then it went positive. Went positive, then negative. See what I mean? What's happening at all the relative extrema? The derivative is changing sign. And I was going to write here where a derivative goes from positive to negative or negative to positive, but let's just make one statement. F prime changes sign. So when you are looking for relative extrema, your process is going to be really similar. You're going to make a sign chart. And anywhere the derivative changes sign, you might have a relative max or min. You might say, why did she say might? You'll see. So on the next page, the test that we run for this is called the first derivative test. How do I find where there's maxes and mins when I don't know what the graph looks like? And the answer is you look for sign changes in the derivative. How do I look for them? Well, again, you find all your critical points, you test them in your derivative, and if it's a minimum, you would have been going down and then up. And that's what happens on your sign chart. If it was a maximum there, you would have been going uphill and then downhill. And that's what would happen on your sign chart. So if nothing happened there in terms of a sign change, boom, boom. Let's suppose the derivative was 0 at these places too. Let's go like that. What do you think the graph would be on this interval in this situation where it went negative, 0, negative? What do you think it looks like? Going down, then what happened? Went a little bit, right? And then what? Down again. Exactly. This scenario graphically goes like this. It's going downhill, has a derivative of 0, and continues to go downhill. It's like a ski slope. You know what I mean? So this would provide you with neither maxes or mins. So let's go show in reverse what you're going to be doing. You're going to be given a function and answer questions about a graph that you can't see. But we're going to practice the other way first. Let's take a graph that you can see and put it in its sign chart. So right here would have been my sign chart. At C, I would have had a derivative. What's the derivative at C? 0. Actually, for each one of these, the derivative was 0 at C. So each one of these, your sign chart would have been like this. And then over in this one, you would have tested to the left over here, and you would have found your derivative to be what? Positive. And then you would have tested to the right, and it would have been negative. And you would have said, hey, there's a max there. See what's going to happen? We're going to take away the graph in just a minute. On this one, your derivatives would have been negative on that interval when you picked your favorite number, and then they would have gone positive. And you would have said, hey, there's a relative min. On this one, what would your sign chart have looked like? Plus, plus. How about over here? Negative, negative. So you have to be careful. True or false? When the derivative is 0, there's a relative max or min. False. Actually, both are false. When there's a relative max or min, the derivative was 0 is also false because that can happen at cusps too. So we have to talk about all the details. Right here is one of the more important things I tell you. If you were taking this in college, and through we're using a college textbook, but you're taking AP and there's some fine differences. One is you guys need to know how to write your answers for FRQs. When I was in college, I could just go like this, rel min at x equals 3, and I got the right answer. But for you guys, you have to write y. So let's make a fake situation. Little Jensen makes a sign line. He determines that the derivative was 0 at 3. And so he goes like this. And then he goes and tests his favorite number over here on the left, and he got a negative for his derivative. And then he goes and tests his favorite number to the right, and he got a positive. And the question on the free response was, locate or find where there are any relative extrema. And in his brain, he'd say, okay, this means that there was a relative what there? Min. But if he just writes rel min, he doesn't get a point, nothing, because that could be a guess, right? It could be a 1 out of 3. It either is rel min, rel max, or neither. So that's not good enough. So then he says there's a relative min at x equals 3 because the sign changes. That's still not good enough. Why not? Why would that not be good enough? It could have been a max. So you have to say how the sign changes. But then there's even more to it. So then he writes, he's getting better, right, Jensen? You're getting better. So then he refines it to there's a relative minimum at x equals 3 because the sign of it changes from negative to positive. He's got more points. You can't say it, because we're going to have 3 different things running with these problems. The original, the derivative, and the second derivative. And they can all be used to answer the question if you word it right. So watch. Here's the way most kids would do this. They would say, there is, when it says justify, you need a sentence. A relative what? Min. You can't just say relative extrema because I want to know which. Relative minimum, I'm just going to abbreviate min. At, and you can use the at symbol, that's fine. X equals 3, and then you have to say y, and you can't point at the sign line. They're not, sign lines and graphs are not given any look at whatever. They read, they don't look. So, because f prime, not it, because f prime does what? Changes. And don't say changes sign. Changes from what, Jared? Yeah, from negative to positive. And this would be what most kids write. But watch me change the wording and still have a completely good answer. You don't do this in your notes, so it'll make a mess. If I decide to talk about f, not f prime, and so I make the subject of my sentence f, I could still say that there's a minimum here, but I would say because f goes from decreasing to what? Increasing. Do you see the difference? So you can't, that's perfectly valid too. You can't say because f changes sign. Do you get why? So it's f prime changes sign or f itself changes from decreasing to increasing. Either one is acceptable, but always do it the same so you don't mess with your head. I would talk about f prime because that's what your chart's on. So we're going to go do 3 of them and we'll be done. On the next page, we've got 3. By the way, we're doing these all with f, but later in the year, these actually represent something, like their actual rates of change of things changing over time. Usually, we call them rate in, rate out problems. So you have stuff going in and stuff going out. And you can only have a maximum when that changes from positive to negative. And so, or negative to positive, either one for maxes and mins. I'm off a page. One more. Come on. What in the world? Why is it skipping a page? Oh, that's because I didn't erase it last hour, so I wasn't thinking. All right, so here's your next page. I will erase it from last hour. And we are going to find the relative extrema. Go underline that word, because there's a difference. And I'm going to repeat it one more time. We have no homework, so you can give me the rest of your day and then no more calculus till tomorrow. What if it had said, find the extrema? Not relative, the extrema. What would you do? You would plug 2 pi into the function. You'd plug 0 into the function. You'd find where the derivative equals 0. You'd plug those in, and the biggest one is your max. The smallest is your min, and you'd be done. That's not what this question is. It's relative. All right, so what am I going to do? The first thing I do is I look at that, and I ask myself, are there any issues with the function itself? And ask, most of the time, that's the answer. There's no discontinuities, no asymptotes, no holes, and honestly, the difference between that is the difference between an A and a B, not passing or failing. The person who neglects the details can still get a B, actually, but you're not going to get an A, because like these two have issues and you won't spot them. Most of them don't have issues, though, so you'd be safe. So let's go up here. This one has no issues in the original function, so I can assume that that function is continuous. The next thing I do is I take its derivative. All right, so I take the derivative, Annika. What's the derivative of sine? Yes, and then I ask myself, does the derivative have any issues? Yes or no? No. So now I know not only are there no asymptotes or no holes, there's also no cusps or vertical tangents. So really what I know is I have a roly-poly smooth function. Fair enough? So on that roly-poly smooth function, I just need to find where the derivative is 0. And that'll tell me every place it possibly turns, which means that's where cosine would have to equal a half. And then I go, oh man, it's the unit circle again. I hate it. You still need to use it all year, every chapter, so get good at it. Make a cheater. And here's your thought process. Since the cosine is positive, and cosine means the x value, I know I'm to the left, right? So I'm over this way. Whoops, I'm moving the whole thing. Uh-oh. I think my smartboard died. Oh, no. It's back in business. All right, so I know I'm over here. How many answers am I going to get? 2. 1 in the first quadrant and 1 in the fourth quadrant. Are you with me? This is my thought process. Hopefully it's faster for you guys than how I'm talking about it. I know it's not at pi over 4 because those are the root 2's over 2's. So I'm now down to 2 options. It's either pi over 6 or 2 pi over 6. It's one of those in the first quadrant. You could actually go by looks and you'd probably get it right. Which one looks like it's halfway over? The pi over 6 or the 2 pi over 6? Yeah, you can almost see that that's halfway over. But I always memorize that the sign of the first one, pi over 6, is a half. And if that's the only one you know, you get all the others for free. Just switch it up at the, oh, my smartboard's not liking all the recording. Can you feel it? It's starting to bog down. Anyway, what would be one of the angles? Pi over 3. Now you go find the other one. I want you to be really good at finding the one that's down here in this quadrant, and then we'll talk about how you get that. Oh, come on. I think my smartboard's dead. Maybe it'll write in blue. No. It's not. I'm almost done. I'm going to let it rest for a moment. So you guys raise your hand when you found the angle down there in the fourth quadrant. It's got the same gap with the x-axis. That one went up, pi over 6 and another pi over 6. This one has to go down, right? What is it? 10 pi over 6 or 5 pi over 3. That is the correct answer. Exactly. And again, if that bugs you, you have to be able to think it out. There are 6 pi 6 to here, 12 pi 6 to here. I need to go back 2 of them. So I'm at 10 pi over 6 or 5 pi over 3. So there's some candidates. For my roly-poly function, I've got these that need to be tested. So I go here. I know I'm testing them in the derivative. I put them on here, pi over 3, 5 pi over 3, and I know the derivative was 0, so I know it's a smooth exchange. It's not a cusp, right? It's a good one. It's a nice smooth exchange. What do I do now? I test, and I'm nice to myself. I test my favorite unit circle angle over here, because I take its cosine. What's the easiest thing over here to take cosine of? 0. Cosine of 0 is 1. A half minus 1 is negative. I know it's negative over there, right? Next, I go to my favorite angle in between those to find the cosine of. What would be a really easy one? Pi would be great. Cosine pi is -1, so I'd be adding. That would be positive. By the way, I kind of know it's going to alternate just because I know it's sine wavy. So I could actually, it doesn't always alternate, but that one's kind of obvious, right? So when I answer the question, I'm not going to write it on here. Relative extrema. I now know there's a relative what at pi thirds? Relative. It's going down and then up. Minimum. And at 5 pi thirds, there's a relative maximum. Okay? And if you had to say why, you would say because f prime changed from negative to positive at pi over 3 and from positive to negative. Or if you're talking about f. You could say because f went from what? Help me. Decreasing. Yeah, there you go. You guys are good. All right. So I know it's the end of the day and I've been talking a lot, but these two are the most important two because these two are the difference between the A and the B. I didn't say between an A and an F, but these two right here do have issues that need to be discussed. On the other ones, there were no issues. So we have to talk about what the issue is and how you deal with it. Look at that function, the first one. There's an issue with the function itself. Where's the issue? 0. Then you have to decide what, you know there's a discontinuity there. So I'm going to write that on here. There's a discontinuity at x equals 0. I need to figure out what kind it is and what happens there, or I'm going to get the answer wrong. So is it a whole, because there's only two kinds really. Is there a whole or an asymptote? How do you know it's a whole? It's removable. Yeah, you could factor out an x and cancel it. Really, this is x squared plus 1, just not at 0. truly. So if I really get it, I don't even need to do a sign line or anything. That's why I said if you really get this chapter, it's kind of easy because you're just going, hey, that's a parabola with a hole right here. So stupid question because there's no relative extrema, right? Why not? Because I can't get there. However, this is what 9 out of 10 dentists have found. Ready? That most kids do this. They ignore the fact that there's an issue, right? They go, if it makes a heart, break it apart, and they get x squared plus 1. That's right, correct? They then take the derivative and they call it twice x, right? They then find where the derivative is 0. Where's the derivative at 0? 0. They go make a sign line because their teacher taught them to. They test to the left, right? They test to the left. And what do they get? In the derivative, negative. And then they test to the right and they get a positive. And they go as decreasing and increasing. So there's a relative min. And that's not true. Because what happens at the issue? There's a what? Hole. So you got to be really careful. This thought process and work is fine, but always write what's going on there. And I'd write the word hole over it. All right? If there's either a cusp or a vertical tangent, I draw one of those so you don't forget. Watch an entirely different issue over here. This one's a good problem, and it's difficult. And there's an issue that really matters. Where's the issue? 0 again. All right, so tune in, last one, and then you have 10 minutes to just sit and chat. There's a discontinuity to x equals 0. Is it removable? Does it cancel out? Factor cancel? No. So what is it? That's important because you can certainly go from increasing to decreasing at an asymptote, but do you have a relative max or min? So when you make your sign line for it, I'm going to go put it down here. You do need to put 0 on there because it's a game changer, but put an infinity symbol over it. Why do I say that? So you know that when you're done with the problem, you know what's going on there. This is important. What's going on at 0? Asymptote, or if you even want to draw one, or if you wanted to go like this, but don't put a 0 above there. I can't have a relative max or min here, regardless of sign change. All right, so then what do I do is I go take the derivative, because I have to find where the derivative is 0 or doesn't exist. So what I would suggest you do is break that apart, but be careful. Make sure you see that negative, let's go throw it in the basement, so you can see that that's a negative x squared, and then that's, what would it be? Minus x to the negative 2. Watch my signs. Am I good? Yes. Ready to take a derivative, Mary, quite contrary? What's the derivative of f? Negative 2x, then what? Plus 2x to the, did you say 2 over? Yes, 2 over x cubed. You might say, oh, there's an issue with the derivative at 0. I already knew there's an issue at 0, so no worries, right? Nothing more to do on my graph. I want to know where the derivative is 0, though, which means I need to get this as a single fraction. How do you get this as a single fraction? Because the only way a fraction can be 0 is if the top is 0. I need to see the top. How do I get this as a single fraction? Crisscross applesauce. Yep, so let's go do that. That would be negative 2x to the 4th plus 2 over x cubed. There's my derivative set equal to 0. You might say, yeah, but issue, already got it, locked and loaded. I need to know where the top equals 0, either because I can see it, or I know it, or I keep factoring. You guys go find where the top equals 0. Set it equal to 0 and solve, factor it, or use common sense. But if you use common sense, don't forget, you'll miss an answer, some of you. So you got to be careful, right, Jared? I just saw you nod. There are 2 places where the numerator is equal to 0. Where are they? 1 and negative 1. I always say take the time to factor because that would be x squared minus 1 times x squared plus 1. And then this goes farther and you'll get the 2. But on my sign line goes a 1 and a negative 1. And I know that it was 0. Now I have to decide what happened there. Did it go up and down, up and keep going up? So I test. Are you ready? Last up, I run a test. What am I testing in? The sign of the derivative. So you need to go find your derivative and you need to run a test. And you might say, well, do I do it here or down here? The answer is yes. Pick one. Whatever looks the best. I like it factored, so I like to go down here. If I throw a negative number, like -2, into here, I'll have a negative, right? Then what will I have? I'll have the negative, and then I'll have a, what? Positive, and then another positive, but remember it was all over x cubed as well. I just didn't write the denominator. This is going to be positive. And then just trust me, it goes like this. Negative, positive, positive, negative, positive, negative. If you were careful, that's what it does. So let's talk about what the graph looks like. Somebody take out their graphing calculator, and I will tell you, I already know what you're going to have. All right? You can kind of guess. Take out your graphing calculator. Who has one sitting right out on their desk? Go enter the original function, and I guarantee this is what's going to happen. It's asymptotic at x equals 0. It goes up and then down at -1. I just don't know where it peaks out because I didn't actually find the y value. So can someone just tell me, does it peak out above or below here? Just so I can see it. I'll wait till someone graphs it. And I know at 1, something similar is going on. I'm going to wait. I think you've got it entered wrong. It was a negative out front of that. Insert a negative. So, but now that helped me because it's just going to flip that over. It looks like this. All right, when he graphed it. So look, the derivatives are positive, then they're negative. Doesn't exist. Positive again, negative again. So the answer to the question would be there's a relative what at -1? Relative max. And a what at 1? Relative max, and most kids will answer with a third thing because they'll forget the detail and they'll see this sign change right here, and what will they say happens right here? They'll say there's a relative min because they see it going from decreasing to increasing, but it's asymptotically doing so. What do you think? Yes? Yes. If it asked for absolute max, it would be a tie. You would say it is whatever this is at -1 and 1. You'd give the location of both. We are done. For those of you who want to make sure you don't have any homework for the weekend, tomorrow you will have an assignment that you won't finish in class, but you'll get a huge chunk of time. You will finish it in class if you come in with that part of it done. So that's half of it. It's the half you could answer right now. And then I'm going to give you a little bit more notes tomorrow. But honestly, it's not due till Monday. Done.